Hello, and in this video we're going to be looking into whether a function has an inverse. This is still section 5.2. We're going to try to answer this question: do all functions have inverses? So is this always true? So what we're going to do is we're going to investigate the function f of x equals x squared, and we're going to find its inverse. So the question is, if we create an inverse, to create an inverse, we need to swap the x and y values. So that's what we're going to be doing here to create this inverse. So we'll start here at the center, or the vertex of this graph. 0, 0 would still be 0, 0 when we swap it. So 0, 0 stays at 0, 0. Now this point here, 1, 1, it also stays at 1, 1 because we swap 1, 1, we still get 1, 1. Now my next point along x squared here, that's a complete or a whole value, would be 2, 4. If we swap 2, 4, we should get 4, 2. So 4, 2 would go right here. So its inverse value would be right here, 4, 2. If we went to the next value here, that would be 3, 9. 3, 9 swaps to 9, 3. So 9, 3 would be its value right here, 9, 3. Now we want to continue graphing these going backwards on the graph as well. Let's go on the negative side. We have negative 1, 1. So that would swap out to 1, negative 1, which would be right here. 1, negative 1. And its next value here is negative 2, 4. There are other values in between, but that's the next whole number value. So we're going to go to negative 2, 4. So that means we're going to go to 4, negative 2, which is right here. 4, negative 2. And then our final value I see on this graph right here, that's a whole number value, is negative 3, or an integer value is negative 3, negative 9, or positive 9. So that's 9, negative 3. So if we look at this function, or this inverse, if we look at the graph of the inverse, it's going to curve from here all the way down to here, and then go back and go the other way. It's going to curve all the way back to here and out to there. So this is our inverse graph. Now if we look at this graph of the inverse, we don't actually have a function. This is not a function, because a function only has one y value for every x value. And if we look at, even if we just look at the points I graphed, 9, 3 and 9, negative 3 are not going to be in a function together because they have two outputs for the same input. And this does not pass the vertical line test. If we draw a vertical line, let's see, edit, undo. If we draw a vertical line, it doesn't cross once. It crosses twice. So it doesn't pass the vertical line test. So not a function, doesn't pass vertical line test. So the inverse is not a function. We could conceivably make this a function by eliminating part of the graph. So if we were to actually take this part of the graph here and eliminate it from our function, if we were to eliminate this part of the graph from our function, and that would eliminate this part of the graph of the other function, this would kind of match up with the inverse. The inverse, we would think the inverse of this would be f negative 1 of x equals the square root of x, because the square root undoes the square, so we would think this is what we would want for an inverse function. But if we look at the square root of x, we only get this piece. So what we have to do is we have to restrict our domain on our function in order to get the inverse to be a function. To get it to be a function, we have to restrict domain on the regular function, on f of x. We have to restrict the domain and say x has got to be greater than or equal to 0. In order for this to occur, we have to cut our domain or on our function in order for it to be a function when we graph the inverse. Now how do we, so what we're saying here is that this function, or this function that we started with, does not have an inverse unless we restrict the domain. Now we want to take a look at what types of functions have inverses. So we have a specific type of function that have inverses, and those are called one-to-one functions. One-to-one functions are a function that has each element in the range is paired with exactly one element in the domain. So each element in the range, so let's say my element in the range is 9 here. So if we pair that with an x value, then there's only going to be one x value that's paired with this value of 9. Well, in this case it doesn't, because 9 also has a value over here on the range of this function. So 9 is paired with 2 domain elements. Okay, we have 2 domain elements. In the previous one you could see that there's 2 domain elements. There was 3, 9 and negative 3, 9. So this range element is paired with 2 domain elements, so it's not one-to-one. This is not one-to-one. Okay, so to be one-to-one means that you only have one pairing there. Now, we could show that it's one-to-one by having a horizontal line cross only once. So that's called the horizontal line test. So a horizontal line test is if a horizontal line passes through the graph one time, then it's one-to-one and it has an inverse. So if we were to draw a horizontal line here, in several places, we have 2 places. That's why it's not one-to-one. As I wrote up here as well, it's not one-to-one because we have that horizontal line, and that's the test that we use on a graph. The graph is drawing a horizontal line, having it cross once. So in this case, this one is one-to-one, and it has an inverse. That doesn't have a restricted domain. So anywhere I draw a horizontal line, I only get a crossing of one thing. So on the second example, if I draw a horizontal line here, it crosses once. But if I go down a little further and draw a horizontal line, we get it crossing 3 times. So this is not one-to-one. So that means it doesn't have an inverse. Unless we restrict our domain of the original function. If we cut this graph so that we could only get a crossing at once, we'd have to cut it maybe right here. So we could go from here to here on the function. We could go from here to here on the function. We could go from here to here on the function. As long as we don't have something that turns back around on itself. So it doesn't have an inverse unless we restrict the domain, and that would change the function if we restricted the domain. So we would just say it doesn't have an inverse. Now, we could see here this one also doesn't have an inverse. We could just look at the x-axis, It crosses 1, 2, 3, 4 times. So this is not 1 to 1 also. Not 1 to 1. And it doesn't have an inverse. So what we're doing here is we're looking at when there's only one X element, one domain element for every Y or every range element. So if we can draw a horizontal line and we get it to cross just once, that means it is 1 to 1. If we get it to cross more than once, then it's not 1 to 1. Now, 1 to 1 functions are important because that tells you whether you can have, we have an existence of an inverse. So there is an inverse and we can define it. So without restricting the domain. So this function, f of x equals x squared, doesn't have an inverse unless we restrict the domain and say that we're only going to take the values greater than 0, greater than or equal to 0. Then it does have an inverse. And we could do that with any function that we have as long as we restrict the domain. But in general, we do not restrict the domain, so therefore there isn't a inverse if the function doesn't pass the horizontal line test.